fluids that obey a linear relation between shear stress and rate of strain are called Newtonian fluids. Okay, so by and large, we are concerned with Newtonian fluids. As you can see, there is a flow in this direction which changes in this direction. That's a definition of shear, right? It's the rate of deformity, right? And that has to be maintained if there is some sort of viscosity in the fluid. It turns out that for most purposes in astrophysics, when there are no solid walls, okay, you can ignore this boundary layer, so-called boundary layer, where this viscous effects are most important. So if you are in the bulk, so when you hear terminologies like bulk and boundary layer, bulk means the fluid occupying regions that are far from the walls of solid surfaces. Boundary condition for ideal fluids was that the normal component vanishes. In this case, the total velocity must vanish at the solid surface, or the relative velocity between the solid surface and the fluid is zero. Okay. For example, you see the fan collecting dust. That's typical examples people give. Fan is moving at high speed, but it collects dust. So whenever dust particle hits the surface, it sticks there because there is no relative motion possible. Okay. There is viscosity in the medium. Every medium near the walls, it will have viscosity will play a very important role near the walls. But in astrophysics, there is hardly any wall, so you can forget about it for now. Although it is very important term, you can look up one reference, this person, life at low Reynolds number. Okay. That's a very interesting article, and you see and convince yourself that does inertia matter at low Reynolds numbers? If there are motions at very slow speed, does it even matter the inertia, that how massive the object is? So pulling a ball and pulling a whole ship, basically the mass drops out from the ground. So inertia. So, but anyway, you read about it. The Reynolds number, which characterizes how turbulent or viscous the fluid is basically given by these are the inertial terms. These are, say, the pressure terms, body force, and this is the viscous force. So if you take the ratio of inertial force to viscous force, the inertial force is this term. In case of high velocity, high Reynolds number, this is the term that dominates. Okay, even in the steady state, when you can forget about that. Suppose this is the term to take care of. So this is like V square divided by L type of order. So it's quite often that you will see people writing what is an order of magnitude of this term. In astrophysics, order of magnitude is very important. So the order of magnitude, this is like a gradient which is acting over a certain scale, right? So it gives you a scale. So the order of magnitude is roughly V square divided by some typical length scale of the problem. That could be your scale of the supernova, okay? Or any system, scale of convection, can be anything. For different systems, every system basically is governed essentially by this type of equation, any system. So it's very general, so you can be very liberal while thinking about it. Okay. Similarly, the viscous term is of order viscosity, which is a property of the fluid. It can be very small, but it is there, and it makes a whole lot of difference. I'll just show an example. I quickly want to go to magnetic field. So if I take this is of order this side. I take the ratio, you get a quantity which is dimensionless. After all, these are all what? Force per unit mass, right? Yeah. So you take the ratio, you get a dimensionless quantity. It is useful to define dimensionless quantities so that you are not bothered about what scale this scale or what is the value in speed and stuff. That doesn't matter. So long as the Reynolds number, if this is your control parameter, you can perform a controlled experiment of, say, a ship or a aircraft in your lab, and so long as the Reynolds number in the lab is maintained at a value which you see, for example, in the aircraft, real aircraft, the behavior of the fluid you can assume as going to be identical in these two cases. Okay, so you can model the fluid in a completely independent setting or environment. Doesn't matter whether it's a small or big. Yeah, scales drop out essentially. So long as the Reynolds number, if this is the control parameter. It turns out that this is a very good control parameter. Okay. So as you can see, this is a dimensionless number, and if I want to go to very large values of Reynolds number, many ways you go to a very high speed, or you go to very large length scales, very small viscosity. Any of this or all of this will give you very large values of Reynolds number. All of that is true in astrophysics. Okay. Typical Reynolds number of the sun is 10 to the 13. A swimmer, given the viscosity of say water, is 10 to the 4, which is highly turbulent. So as you see, if this number is large, these effects, the non-linear effects are very, right? I mean, you are taking ratio of this to this. So if large Reynolds number, this non-linearity is going to play a very major role. I asked you a question about fan you switch off and you experience about seconds, or maybe less than a second, for the air circulation to stop in the room. And if you take the usual viscosity, the number you will get is about 11 days. What changes? The air in this room is highly turbulent. It's of this order, Reynolds numbers. So whenever you see high Reynolds number, you see that non-linearities are very important. Simple decay time scale. We determine a decay time scale from this term, right? But if the Reynolds number is large, this term is not even important, right? So typically, the so-called dissipative term is not governing a dynamics or decay if the Reynolds number is very large. And that is the case in most objects. So then clearly you must determine the decay time scale from this term and not from this term. And that is the term of key to dissipation. Okay. Low RE fluids are basically called also Stokes regime. These are reversible flows. As soon as you go to a turbulent regime, everything is chaotic, loss of predictability and everything. They're highly chaotic flows. Microorganisms that are swimming, they tend to be in a very low RE system, and that is very much important. That is actually essentially, as you will see in this life at low Reynolds numbers, keep life out. So, if I look at flows at different Reynolds number, and as we go to larger and larger values, this is nothing but a flow past a cylinder. Just to impose a flow of constant speed from all this, or make sure that your Reynolds number is changing. Okay, it doesn't matter how you change the Reynolds number. You just change it because that is the only control parameter. Yeah? So I take a flow past a cylinder at very low Reynolds number. Flow is symmetric, reversible. At nearly zero Reynolds number, you can find that this and this side are essentially symmetric points. There is stagnation points here. As you increase the Reynolds number, you see the development of eddies, right? Higher and higher Reynolds number. But one way to increase the Reynolds number is to basically go to limit of infinite viscosity, right? Sorry, limit to zero viscosity. Zero viscosity is an ideal. Now I am going to higher Reynolds numbers. Okay, effectively viscosity is getting slowly unimportant. It seems so, but it's very puzzling. Okay, the reason I'm showing you this, guess what will happen if I go to the limit of highest Reynolds number. That means say nu equal to zero limit. So nu tends to zero, and nu equal to zero. Okay, there is no correspondence in the solution. These two cases. Nu equal to zero. What you get is this symmetric flow, ideal fluid. Okay, nu tends to zero. You get something like this. You keep increasing the Reynolds number. It is never zero. However, infinitesimally small it is, but it will give the flow. It will make the flow very turbulent. This is already just 10 to the 6. There are a lot of lab experiments, and the key to all the diverse things that you see in nature ultimately is all connected to this turbulence, in a sense. Okay. Nothing is laminar. So the other regime low Reynolds number is laminar. So we will stop there. Okay. Just note that any system, if this is your Fourier mode K, which is basically inverse length, yeah? These are small scale, these are large scale, and typically you would see that if you measure a kinetic energy in a given Fourier mode K. Suppose supernova is injecting energy, yeah, in a galaxy. Galaxy is 20 kiloparsec. Supernova is about say 100 parsec. It's still small scale, but 100 parsec, there is a lot of range of scale available below that 100 parsec. Right? So if you inject energy at this one scale, there is a single eddy supernova which is injecting energy all over the galaxy. Right? What happens that because of the turbulent interactions, there is a cascade of energy from large scale to small scale. Okay, energy cascades with a power law which is k to the minus 5 third. This is the Kolmogorov. I'm just mentioning these things so that you are aware that such things are there and later can read about it. This is an unsolved problem, only phenomenology is problem. That it has, this is a log scale. This is a log, this is a log. So only in a log you see, you convince yourself that you get a straight line for a power law. Right? It's a power law, k to the minus 5 third. When you take any power law in a log scale, like something like if y varies as x to the alpha, so I can take log y equal to alpha log x, right? So in an axis log y versus log x, it's simply a line. Alpha is simply a slope. Right? So it's a straight line equation. So whenever you have a curve or a function which behaves as a power law, you must take log when you want to display your results. When something is exponential, you take log on one side and not on the other side. Then also you get exponential. So better presenting your results. So energy that is injected cascades to smaller length scales. Yeah, that's called a forward or a direct cascade. Okay? That is happening in this room, by the way. That is why the motion immediately stops. Fan injected energy, it can be supernova or the fan. The phenomenon is identical. The energy injected at large length scale cascades quickly because of non-linear interactions, U dot gravity. That is, in principle, not so difficult to understand. If you imagine V as some sort of a sine, yeah, interaction meaning non-linearly V times V, right? So I can write this as product of sines. So I have motion only at K. So now you apply your two cos of some two cos of difference and all that. So this interaction, meaning colliding eddies, will make you, you started from a single Fourier K and you produce what? 2K, right? Something like that. 2K and 0. So you're with each K, what will you write? Sin Kx into sin Kx. What is the formula? What happens? You'll get a 0 mode and you'll get, now I'm also confused. Then we'll give you another K. Yeah. Does anyone remember? Sin or cos? Huh? So what happens to the K? Huh? So anyway, look up. I forget.
Cos 2K. Cos 2K minus cos 0.1.
Okay. So yeah, so you have created 2K mode, right? So from K you have gone to 2K. Similarly cascade, but this is too simplistic. Nature is even more complicated. And then at some scale of viscosity, which was not very important in the bulk, that viscosity will kill that power and you get an exponential cutoff. This is your Kolmogorov spectrum. For a dynamo, for MHD, we will be interested in an inverse cascade problem. The reason I am drawing is that you want to inject energy at a supernova scale and you want to see a buildup of magnetic energy at a system scale. That's a completely different problem. Forward cascade is more natural. What is happening here when your fan is turned off, the energy cascade time there is very small. And that can be worked out. That turns out to be a photosynthesis. In fact, the cascade time there, you can see, is roughly 1/3 of, just work out the number, L by B. Something like that. Not 1/3 is also not bigger. I think I will write, yeah, L by B is dimensionally fine, right? So this is of order that. So if you now work out number of velocity, and length scale. There is no viscosity playing role. That is the relevant decay time in the non-linear case, which is what is happening. And then it will give you something like seconds. Okay. But just keep in mind that there is always at high Reynolds number. This is a situation which is generic to any field. Okay. You inject energy at one scale, multiple whole spectrum is created. You didn't inject any energy here, but that's the shape invariant inertial range that is maintained. Viscosity is dissipating that energy that is injecting. So if you keep on injecting, the dissipation rate and injection rate will become same in the steady state, maintaining slope. Okay. So even if you don't resolve or you don't study this scale, so long as the spectrum is maintained, you can comment on this scale simply by looking at this scale, because all the scales are well connected. You didn't do anything at other scales. You supernovae or a fan was working to create this scale. The whole spectrum is created just by nonlinear. Okay. So it's very impressive. The goal of similarly, I can look at the energy in the magnetic fields at different scales. Scales you should begin to think in terms of a scale that if I give you field, yeah, it can be single sinusoid. A single sinusoid means it has only single scale. Right? Okay, Fourier module. If I give you an arbitrary function, you can write in terms of summation over all Fourier components, right? Infinite Fourier components. That means each of those Fourier components represent a single scale in the problem. Okay. So it so happens that turbulence inherently makes a broad spectrum, that gives you broad spectrum, and our interest is any field that you are seeing, no matter what scale you observe, any system in astrophysics. At every scale you find the quantity is finite. If you look at a system scale, you get a microgauss magnetic field. Nothing is injecting or maintaining that magnetic field. There is no current that is, I can always drive a current here and generate magnetic field here. But for galaxy, who is driving the current at a galactic state? It has to be all self-sustained, internally driven. Right? Energy that is injected in the system is at this scale, and you are interested to see a build-up at this scale. So this is much smaller scale, right? Much larger scale. Forward cascade is somewhat understood. Inverse cascade is slightly non-intuitive, somewhat different. So we will discuss this. So how do you take energy from here, put it into a different field? Energy meaning this is in motions, right? You want to not only convert it into the magnetic field, you want to put it at a larger scale as well. So quite a high demand. Okay. So let's look at now those kind of things. So system is turbulent. There is viscosity, but very small. Reynolds numbers are large. That's your typical astrophysics. Okay. This is only fluid Reynolds number. Will come to magnetic Reynolds number. That is also very large. These are the different control parameters of the system. Large means turbulent. So now, just some impressions that no matter where in universe you see, at whatever is the scale, this can be a bar magnet in your lab, but for the sun there is no bar magnet. Yeah? So the nature of magnetic field or the way it is driven is completely different. But the point is, if you go to 1 meter, Earth is about 10,000 kilometers. Yeah, these are the auroras you see. Yeah, sun is about 1,000 megameter. You see the solar magnetic field showing a 11-year cycle. See, each sunspot can be larger than the size of the Earth. Such huge magnetic field. Yeah, this is just Gauss level. This is a kilo Gauss level. Powerful magnets, right? Solar sunspot is the first example of magnetic field outside the Earth. Okay, only 1908. But nevertheless, but that was 1908. From there to now, wherever people have looked, at whatever scale, arbitrarily large scale, at the scale of the universe, megaparsec. Scale of the universe is what? Roughly megaparsec, not very big. It's at least it's one can calculate. Yeah, it's countable. So you go to the sun at distance, which is one astronomical unit. The whole interplanetary medium is filled with magnet. You measure it. You go to galactic scale, it's 10 kiloparsec. And these are the synchrotron emission maps. Somebody covered synchrotron for you? Synchrotron requires what? Relativistic. They are relativistic particles, charged particles gyrating in magnetic field, right? So if you see a synchrotron emission, That you can tell by the spectrum, right? Spectrum must have been covered. So if you just look at the mission, JMRT is looking, you are going to JMRT, they are observing synchrotron all the time. That is what they observe. Okay. So, one of the things they observe. So, synchrotron is simply a proxy for magnetic field. If there is magnetic field, only then you will see a synchrotron, right? Now, one can reconstruct the magnetic field maps of a galaxy, and you can see these arrows, but that also you must have seen that you can't tell. Maybe a transverse magnetic field, but you can't tell it's pointing this way or that way. Okay, you need further observation to actually point. But if you look at the arrows, which are the local directions of magnetic field, this is a real image. Yeah, the galaxy. See how ordered the field is. Yeah, I can put a single line threading the entire galaxy, and that is the whole magnetic field. It's a micro Gauss field. The whole galaxy, what you see is a very coherent, uniform magnetic field all over the galaxy. That has puzzled people. It is still not fully understood how, but we will sketch how, at least in modern times, we try to understand this. But it should puzzle you already that whatever you are doing in galaxy, you are doing at a scale of the stars, right? Injecting energy. You want to build a magnetic field. If the galaxy was formed with a magnetic field, the galactic lifetime, how old are typical galaxies, planet galaxies? Roughly? Hmm? Yeah. So the galaxies are about giga-year old, right? Few giga-year old. Giga-year-old galaxy, if you were to again do the same exercise of dissipating anything, right? Anything you can dissipate. Magnetic field is also an energy. Plasma has resistivity, just like fluid has viscosity. If you determine the decay time scale, you'll find that okay, it's larger than the age of the universe. But I said that the Reynolds numbers are large, so the decay time scale is relevant decay time scale, several decay time scale. That is on the order of mega year, 3 orders of magnitude smaller. So even if the galaxy was born for some reason with the field, today you should not see any magnetic, but it is there. So what is maintaining it? What is producing that magnetic? That's the question we are going to be interested. Now you can go a little further, and there are images you can look up Virgo clusters, intergalactic medium at megaparsec scale. In fact, I should have put up a picture of, or you look up cosmic voids. There are cosmic voids where there is uh, no visible matter, no baryonic matter there. These are cosmic voids, and there are enough observations of void magnetic fields. You can wonder how do you detect them. That itself is an interesting story. Read about some blazar observations and detecting magnetic fields in the cosmic voids. Well-known techniques. So it turns out that even in voids there are magnetic. And so natural question to ask, why is it not dissipating? Why has it not dissipated given the age of the universe? What is maintaining it? What is creating? At that scale where nothing is there. So how do you do something at some scale, at stellar scale or supernova scale, and how do you build some coherent magnetic field at larger scale? So it's a challenging and quite interesting problem. In any case, the universe pretty much everywhere is made up of plasma. You know the plasma is a mixture of ions and electrons that exhibit collective behavior. By collective behavior, all what means? Collective behavior you must have seen, you notice in terms of elasticity. You take one atom, it's not elastic. You put many atoms that form a rubber sheet, becomes elastic. That's a collective behavior. Single atom cannot exhibit a collective. Yeah? So, all you're doing, because the temperatures are very large, or in various objects like go to the interior of the star, yeah, go to the black hole, accretion disk around black hole. Temperatures are very large, millions of degrees Kelvin, right? So if I take a neutral gas of say hydrogen, helium, oxygen, yeah, take a neutral gas and just heat it up, and you keep heating, what will happen? Yeah, the electrons, its outer electrons will be stripped first, and then slowly you keep on increasing the temperature. All the electrons will be stripped off with a mixture of ions and electrons. That's governed by the so-called ISSAA ionization equation. Okay, which will tell you the ratio of number density of ions versus the neutral number density, which interestingly, of course, goes as temperature, right? Interesting factor that you should look up what it means. Of course, when there is nothing left to be ionized, what will you ionise? So ultimately, you get nearly fully ionized plasma in most space plasmas. Again, this is a thing you read later about Debye length, that plus and minus of charges, they will be mixed up together. Right? As soon as I try to separate minus from plus, there will be a local electric field and they'll try to bring them together. Right? Plus and minus will tend to be mixed. Okay? So I can again, just like a fluid element we define, which will be collection of many molecules, now you define a plasma element, which will have many ions and electrons, so that over the plasma element, that's the lowest plasma element, for which you will write equations like velocity, pressure, temperature, all that. That is meant for a plasma element, which is composed of many ions and electrons, so that the element by itself, on an average, is neutral. There is no charge imbalance. Okay. The length scale over which you define, now there is a new length scale in the problem, is Debye length scale. It is possible in this context because the electric fields can be streamed. Right? I can have a plus here. You remember all your electrostatics, magnetostatics, that if I take a plus charge electric field at a given location, you can draw a Gaussian surface and determine your flux of electric field and find electric field at this point. Beyond this, this is a charge plus. Plus, but in plasma, these are all moving charges. A big plus, which is an ion, can be streamed by a bunch of electrons, so that at this distance, as far as your Gaussian surface is concerned, there is no net charge here, so no electric field, right? Yeah. So the electric field, while plus and minus charges exist, electric fields can be streamed out and it can be zero. Right? Magnetic fields will not be able. You will not be able to screen out magnetic. You'll see. Okay. So that's the game, that you go to large enough distance such that the electric field elsewhere is streamed out, call it a Debye length. Collisions are still very important because you are going to be in the limit of fluid only. One could write two fluid problems. Yeah, that write equations for plus and minus. We will write equations for a full plasma element and will not be bothered by this nature of charges, or what plus or minus. Okay? We will not distinguish between charges because the charge imbalance is not even there. Okay? So I can imagine like a piece of the sun. This can be piece of the sun where plus minus are such that at any given, if you take any small element, there is no net charge. Minus can flow in this direction, pluses can flow in this direction. At any given volume, plus and minus will cancel and give you no net charge. No net charge. Plus moving in this direction, minus moving in this direction, both drive current in this direction. Right? So you can drive current while maintaining a charge neutrality. Any current means magnetic field. So electric field can be streamed, magnetic fields can be maintained and created. Motions are there because of, say, convection or plasma kicking the particles. So now you at least get rough idea that I can have a situation where I can short out an electric field. Yeah, shorting out means even if you have plasma, by definition is very highly electrically conductive. Yeah. Charges are in motion, nothing holding them, three particles. And as soon as you create an imbalance here, yeah, plus minus, the local electric field will be shorted out by the electrical conductivity, just as the known J equal to sigma E. That's an Ohm's law, right? So if there is an electric field, there will be a current which is proportional to the electrical conductivity sigma. If sigma is very large, current will be large, charges will come close. Large conductivity, charges will just come close. So even before you realize the charge separation or your time scales of interest, the charges have come close. Right? So any imbalance you create will be killed or shorted out. That's what one means. That is why one talks there is no electric field in the universe. There is only magnetic field in the universe. Yeah, a very bad way of saying it, but because as you must have also seen, if you have done any, you've done special relativity. So in special relativity, you know that the electric field can manifest themselves as a magnetic field in a different frame, and vice versa, right? So one has to be a bit careful when making such sentence. But as you will see, the MHD is a non-relativistic limit. Okay, it's a very funny non-relativistic. Typical non-relativistic limit is, I'm just saying it because yeah, it's the last and will not have much time. Typical relativistic is any term of order velocity by speed of light v by c is killed or thrown, right? And you say that we have recovered a non-relativistic limit dynamics. In MHD or magnetohydrodynamics, you keep the term of order v by c. It is still non-relativistic. You throw only terms of order v square by c square and higher order. Okay. If you throw v by c, you throw all the effects. Okay. So yeah, one has to be careful. Throw the water onto the baby with the water. So that's the Debye length. Another length scale in the problem. Will not go into that. Now there are two possibilities of looking at individual particles. Again, as we saw, particle picture and a fluid picture. We stick to the fluid picture. That means we are interested in the slow dynamics. When you say fluid picture, we are interested in slow dynamics. That time scales are larger than the so-called inverse plasma frequency. Plasma frequency, of course, you can see that I created a charge imbalance there. I mean, if you are interested in those kind of time scale, that's a very short time scale. I'll just work out one number for you in the case of astrophysics. Okay, that's also called the Faraday time scale. If you are interested in time scale that are larger than the Faraday time scale, or length scale that are larger than the much larger Debye length scale, then you can adopt to a fluid picture and forget about individual charges. Let's treat them as a fluid. Just note that they can now support a magnet, but no. Okay. Now the conductivity of it, it's important to know, of course, that the conductivity is large. Conductivity, inverse of conductivity is resistivity. So the plasma is resistive. Just like viscosity dissipates kinetic energy, resistivity will dissipate magnetic energy. Right? So one has to always keep a balance that if there is something generating it, something is also creating. So what is that effect? That comes from the collisions of ions. Right? Resistivity comes from the collisions of ions. Its dependence on temperature is given here. That's the Ohm's law, which is a model which simply linearly relates electric field to electric current in the rest frame of the plasma. Yeah, you should perhaps know, you might know that in the moving frame, yeah, that's why you keep the in the moving frame. I mean, given an electric field or interpretation of electric, if there is a current, you can always interpret that current as electric. That's another thing. So just keep in mind that in the rest frame of the plasma, there is actually no electricity. So if you see a plasma from a different frame in which there are motions, charges are in motion, one can work out and derive it in detail. But I just do it simply. That in the lab frame where there is a moving plasma, you write so this is the generalized Ohm's law, or we call it just Ohm's law. Generalized Ohm's law is something else that we have much different terms. So this is an Ohm's law written in a lab frame where there is motion B in a plasma. Okay. So clearly the conductivity increases with temperature, resistivity therefore decreases with temperature. This is simply C square by 4 by sigma, or just remember it as inverse conductivity is resistivity of plasma, which is what is going to kill the energies in the magnetic field. Viscosity goes as positive power of T. Viscosity is contributed by species, which is contributing maximally to the momentum transfer. Eta and conductivity are contributed maximally by the species that are contributing to the electrical currents. Okay, so in this case it could be electrons, in this case it could be ions. Okay, so different species contribute to different microscopic properties. It turns out that all of these are very, very small for astrophysical basis. Eta and mu, they are both very small. If you look at now sun, CV disk, cataclysmic variables, AGN disk, galaxy clusters. Typical temperatures are here, the densities are here. And just focus on the Reynolds number for any system. The enormous, right? Look at galaxy, 10 to the 18, 29. Highly turbulent system. Fluid Reynolds number is same. Fluid Reynolds number, okay, Prandtl number. We define the magnetic Prandtl number simply mu by eta. One should know these numbers because these are the control parameters of a problem. Prandtl 1, Prandtl larger than 1, and Prandtl less than 1. Even if your systems are highly turbulent, these three regimes of Prandtl are even qualitatively different. Systems like galaxy, though turbulent, and system like sun is also turbulent, but those two systems may have absolutely no correspondence simply because the Prandtl number of a galaxy is larger than 1, Prandtl number of the sun is smaller than 1, and these two exhibit completely different solutions. Okay? So these are added complexities that if your system offers more than one control parameter, the system is very difficult, very tough. Okay? This is your Rn by Re. Re we define with respect to viscosity, that is the fluid Reynolds number. Rm we will define similarly with respect to the resistivity, that's the resistivity of the plasma, right? So if you take the ratio Rm by Re, you get number mu, viscosity divided by resistivity. Resistivity is inverse of conductivity. That gives you the measure of magnetic Prandtl number. Sun, for example, is low Prandtl number system, 10 to the minus 5 Prandtl number system. Typically, as you will later on learn, low Prandtl number systems are much harder. Any system which has lower Prandtl number, these are much harder systems, even if they look simple. Galaxy, on the other hand, has much larger Reynolds number, but also much larger Prandtl number. So, in some sense, Galaxy is the simplest compared to the Sun. So, if you ask me, I'll say Galaxy is easier subject than Sun, just on this level. Okay. So, some of these things are very important to realize the differences. What do you expect? Okay, so why do we need a dynamo? What is a dynamo, by the way? It's nothing but a conversion of kinetic energy into magnetic energy, yeah, without having any electric current at infinity. I can always drive a magnetic here by driving a current at it, okay, but that's not allowed in astrophysics. Yeah? You can do it in your lab here. Here, without driving that, how can I convert so that I can generate a magnetic? But then you ask the question, why do I need to generate? Right? That is the first question to ask. Okay, the universe might be just born with magnetic. A lot of people might be happy. So the reason is the turbulent dissipation rate. It can be resistance, like resistivity of the plasma, turbulent resistivity of the plasma, or viscous, turbulent viscosity of the plasma. They both will roughly exhibit this. That they will go as LV by 3 dimensionally. So this is simply a dimensional argument, but coming from some non-linear thoughts, that the dimension of mu, kinematic viscosity, is same as dimension of resistivity. This is L square P minus 1. Okay. So you just dimensionally construct a number, which is L square P minus 1. All you are given is supernova blasted at certain scale, injected so much of motion. So velocity is known, length scale is known. You construct a roughly an order quantity which will contribute to your dissipation. So that's a dissipation. Stirring length scale can be 100 parsec. Turbulent velocity can be 10 kilometers per second. This is number taken for a supernova. So that's your number for 10 to the 26 centimeters square per second. Decay time now of a magnetic field that could be present, say, over 500 parsecs, say, large magnetic field, 500 parsecs of the discrete height of the galaxy. It will decay in about this time, 5 into 10 to the 18. Galaxy is about 10 to the 10 year old. About. So the galaxy is about 20 decay time scale. That means anything that you started off with would have decayed within the lifetime of the galaxy. Okay? But that is only if you take the right turbulence diffusion, right diffusion. If you took the microscopic diffusion, you will get a number which is 10 to the 20 years. Take this microscopic or ohmic resistivity. These are very tiny numbers, okay, and they may not be relevant. As I argued that for high Reynolds number, inertial terms dominate. Right? So you better determine your quantities from the inertial terms. So similar conclusions for other astrophysical problems. Any object you take, it would have decayed its magnetic field within the lifetime of that system. Okay. So clearly there is a need for a dynamo that you need to convert, maintain, create magnetic field. Okay. That's the need. Enough. So let's now go to the magnetoaerodynamics. Everything will start from Maxwell's equation. Okay. The only thing you would have seen the displacement current term here, right? Yeah, the displacement current term. This is a correction post Maxwell, right? The pre Maxwell's equation are without displacement current, right? And then these were corrected. Yeah, you must have covered it, right? You must have done the why the displacement current is very important. All these experiments will die over them. We will throw it here. Okay. In astrophysics, is not needed. This is needed to be consistent with the special theory of relativity. Okay. But we are looking at a slower dynamics, and as I will argue later, but these things are clear. Right? Divergence E is 0, divergence E is 4 pi times rho, charge density, electric charge density. This is 0 also. I just argued that any charge imbalance that we create will be sorted out. So for astrophysics, we will just ignore this as well. So divergence E is also good. In fact, E itself is. Okay. Or you replace E, or you judge E in terms of current. That's the way to see. Okay. So that's the equation which will give you a dynamical evolution equation for magnetic field. After all, you are interested to see how the magnetic field evolves in time and space. Right? If you are interested in maintaining or making something, you should have a dynamical evolution equation for that quantity. Right? We just argued that we want to maintain magnetic field. So we need a dynamical equation for magnetic field, del V by del T. Okay. That is given by this Maxwell equation. Use the other. That's the standard Ohm's law in a fixed frame of reference from which you observe the plasma. That's where this equation is coming. So eliminate J, yeah, and put it here. This equation has J here, right? For this J, use the Ohm's law and write down the equation, you get this. Okay. Now, when you have a term like this, here, whatever is the factor here, this is a dimension. For this equation, the dimension of this equation is that of electric, right? That means anything that is here, eta by c square, should have a dimension of time, so that time divided by time cancels out, right? At least dimensionally you see that. No? That time scale is called Faraday time scale, eta by c square. Okay? Eta by c square. And that is very small because that is the time scale over which the electric field will change. Okay? And you're not interested in changing electric field. Okay? So this field will change over time scale of eta by c square. And that turns out to be 10 to the minus 14 seconds for ionized plasma. 10 to the minus 14. Okay? You are interested in a mega year time scale, giga year time scale. Yeah? 10 to the minus 14 is too small, right? So you forget it. So that means this term is so small that eta by c square del E by del T, order of this term is much smaller than the rest of the terms. Yeah? Order of this term is much smaller. Okay, and then you throw. So what happens that from Maxwell's equation, that electric, this can be written in terms of these two objects, which I can substitute in this equation. Yeah, del V by del T going as curl of T, I can substitute it back, and I get a dynamical evolution equation for magnetic field del V by del T. It's a partial differential equation, yeah, which has two parts. If I assume eta or plasma which is uniform, which has uniform conductivity throughout the medium, the whole galaxy or whole sun, this eta can be taken out and curl V appeal to divergence V being 0. You can write again heat diffusion type equation that we have seen before, right? Even for the Navier Stokes, the del V by del T and the last term new Laplacian V, these are generically diffusion equations, right? So already by the presence of Laplacian with a positive coefficient here, this is going to dissipate that quantity, okay, in general. But now you've got another term here, curl V cross V, And that can be your best bet that will give you a magnetic field. Okay? This is going to kill it, this may give you. It's not very clear whether it will always give you a magnetic field. Okay? Certain conditions must be made, must be possible at least in systems. This equation, this is the induction equation. Okay? So for all systems, regardless of what part of astrophysics you are interested in, everybody will be looking at just this induction equation to study the evolution of magnetic field in those systems. Magnetic field in the sun, galaxy, accretion disk, clusters of galaxies, everywhere. This is the equation that determines the evolution. That's why it's important. And in such a short time, I had to cover it quickly. There is a lot what one can say about it, but we will stop as far as this equation is concerned. Similar to the Kelvin circulation theorem, okay, where I showed you, right, that your omega, now you remember that the omega, the vorticity, obeyed exactly the same form, right? Del omega by del T for barotropic fluids, only for barotropic fluids, which is not a very bad approximation. Barotropic fluid only means that if I have a pressure isocontour, like this, that pressure isocontour, that on these are the surfaces of pressure isocontours. Yeah? The density isocontours will be parallel to the pressure isocontours. Okay. So this is violated only in the very early universe when you get something like P isosurfaces crossing and rho isosurfaces, and you get something known as Biermann battery term giving you magnetic field, and that can also be used. Okay. But by and large, you can see that just like the pressure varies in, we worked out hydrostatic equilibrium. The pressure varied exponentially as a function of height. Density also varied exponentially as a function of height. If I take a cross section, both pressure and density are same on that cross section. So that means the isocontours are stacked parallel to each other. Yeah. For those fluids, you can imagine as barotropic fluid. For those kind of things, there is no source term. Vorticity and magnetic field have the same generic form for evolution. If I started with zero magnetic field, this equation cannot evolve and give you a magnetic. Zero is a perfectly valid solution of this equation, right? So this equation, for you to give any magnetic field, requires finite C. Only if you have, or your system has a finite C, you can use this equation to evolve and build the magnetic field that you observe. Okay. If you didn't have any, this equation will not produce. Okay. So all that to keep in mind. So there we saw Kelvin circulation theorem that omega, flux of vorticity through any area element was constant, right? The same theorem, because the derivation is identical. In that case, it was Kelvin circulation theorem. In this case, it is Alvin flux freezing theorem. So P by dt of gamma, the capital gamma was 0. The gamma you can write now here like that, P dot ds. It can be a star, yeah, and this is the surface. If I take the total magnetic flux through a bounding surface, yeah, so the flux must be conserved for an ideal plasma. If there is no resistivity, there also it was valid only for zero viscosity, right? Similarly here, without any dissipation, which is perfectly valid for most astrophysics, as I said before. So this must be zero, right? And there we saw, right, that omega, vorticity, was proportional to the stretching. That's how your tornadoes and all got intensified if there is a stretching of tornadoes, right? So similarly, the conclusion will be the magnetic field can also be stretched, and the local values of magnetic intensity can simply increase as a result of stretching. So as a consequence that this must be zero, if I take a star, suppose somebody asks you to explain the origin of neutron star's magnetic field, the first guess could be sun. You start from 1 Gauss speed, yeah, neutron stars have say 10 to 14, 10 to 15, that kind of magnetic field, right? 10 to 12 at least, yeah. So that kind of magnetic field, that order of magnetic field, how do you take? Yeah? So one of the first step would be that you appeal to the flux freezing, that there is no dynamo. Flux freezing is not dynamo by. Dynamo means you are converting from the motions and putting it into magnetic. This doesn't require any conversion. This is the same magnetic field. Okay. It's simply due to the squeezing, which is because of flux conservation, that the flux through this area is how much? I could simply write V times A, right? Just simply write it, V times A. So that is, I can just write now as radius square times P, right? 4 pi r square. So radius square times P is the flux through that surface. Okay, now this must be constant. So if the star goes to a collapse, yeah, and becomes a neutron star or white dwarf, just imagine that it just collapsed, yeah, white dwarf. Okay, so clearly you can write R1 square and R2 square, and you see that because the flux is conserved, if you go to smaller radius, your magnetic field must increase, right? Quadratic to the radius, quadratic part to the radius. So you can work it out. If you went from a megameter, or more than a megameter, 10 to the 6 kilometer, 10 to the 3 megameters, from there to 10 kilometers, say like a neutron star, from some supernova scale to a neutron star scale, if it just collapses, you started off with 1 Gauss magnetic field, very small, tiny magnetic field. Simply as a matter of collapse, you produce 10 to the 10 Gauss. Yeah? Powerful, right? That doesn't end the story, but that should be your first guess. If you want to explain most powerful magnets in the universe, this is your first guess. That it must have gone, at least that is what should first come to mind, that it must have undergone some sort of a collapse phase where a diffuse matter or diffused star may have started off with very small magnetic field. As a result of collapse, you are building up the magnetic field. Because the flux has to be conserved. Area has gone down, magnetic field must go up. One way to produce a magnetic field, right? You're not produced it. So that's somewhat bad way of saying. That I will still not call a dynamo. It doesn't explain all the magnetics. And then if you observe, but this is the maximum you will get from this, right? And if I say that the system has 10 to the 14 Gauss, another 4 order of magnitude is much harder thing. Okay. That requires dynamo. Even 1 order of magnitude larger is much very different problem. But at least you can appreciate that collapse will give you larger magnets. Okay. Fine. So just let's collect some of thoughts on the magnetohydrodynamics. That this is a non-relativistic limit of Maxwell's equation. It's a funny non-relativistic limit where you keep V by C order term and ignore V square by C square order terms. Okay. Plasma is usually modeled as a single fluid. That means plus and minus are not separated. It's a single fluid. Okay. So plus and minus, while maintaining the charge neutrality, can slide past each other, drive current, give you magnetic. Electric fields are not there. There is no electrodynamics, only magnetodynamics. Because the electric fields, if at all there is any, in the rest frame of the plasma will be shorted out. Okay. I can interpret the magnetic field as electric field in any other frame. That can all keep in mind. Lorentz force, total Lorentz force density, is how much? Rho E J cross B, right? If I give you electromagnetic field, Lorentz force you can work out. Q E plus V cross B. That is how typically it's written in textbooks, right? This is a Gaussian unit, that's why you're seeing C and all. So if you are interested in or getting confused with units, look up Jackson. Appendix, I think, covers very nicely the units, different units, Maxwell SI units. This is not even SI unit, this is a Gaussian unit. But anyway, you know that if there is a charge which is subjected to electromagnetic field E and P, the Lorentz force will be that is fine, right? No? Q E plus V cross B, Q times P is like a current, right? And now if I talk about densities, then you will replace Q by rho, and that's what is there. Now if you take the ratio of electric field part to the magnetic field part, you get a term which is V square by C square order. So that means you throw the electric part in the Lorentz force. That means the charges do not feel any electric. Okay? So the electric part of the force is neglected all in MHD. You can go beyond MHD. There are situations where MHD may not apply, But it turns out that for most systems, MST is good enough approximation. Eta going to 0, what was eta? This term, right? That's the resistive term. If I take it to be 0, this becomes an ideal MST problem, and then your flux freezing applies. Then you could say that eta going to 0 in induction equation leads to a flux freezing. That means your fluxes are frozen into the plasma. What does it mean frozen? Frozen plasma, just like circulation. Remember that if I take a tornado was fresh, as you move the entire body or plasma moves from here to here by other mechanisms. Yeah, suppose there is a heat current coming, that's where there is a plasma and something came and pushed that plasma, right? As the plasma will be displaced, it will carry the magnetic field with it. Okay, that is what is called frozen in currents. So the plasma and magnetic fields are frozen. Yeah, there is no slippage of magnetic field through the plasma. Okay. As you can also see, whenever you have seen yesterday in the solar lecture, we talked about little bit solar flares and reconnection and CMEs, right, coronal mass ejections. You can see that if it was strictly frozen, there will be no reconnection possible. Yeah, strictly frozen plasmas will never be, because at some point they have to slip through the plasma to reconnect. Yeah. So V equal to 0, if I put in the induction equation, that means it's called induction equation because this is the term that is an inductive term, this is a dissipative term, and you are interested in building up a magnetic field, so you call it an induction equation. That's the induction term. It may give you growing solutions for magnetic field. You can see that this is a linear in B equation, but it has a product term. It's not strictly a non-linear term. Okay, so it may give an impression that it is simpler than Navier-Stokes. It is actually not so true. Okay, Navier-Stokes has explicit nonlinearity E dot grad E, and that's of course source of all richness we know in any astrophysical object. But product is actually as bad as nonlinear. Bad in the sense it is so difficult that analytically it is almost intractable. Yeah. If you want to do a very serious calculation, we make various approximations. I will also quickly make one. Okay, but just because there are products, they may be thought in terms of colliding sine waves, generating spectrum. We just saw an example, right? That you take two eddies, you collide, you form two eddies of the same wave number, collide and give you higher wave numbers, and that's how the spectrum are generated. That there V was colliding with T, here V can collide with T, and can again give you the spectrum, right? You can start from K1 scale here, K2 scale here, K1 plus K2 by 2, K1 minus K2 by 2, and you keep generating further spectrum. Okay. So, if I start off with B equal to 0, nothing will happen. So, B equal to 0 is a valid solution of the induction equation. So, it always requires a C. Okay. Formally, you define dynamo action as conversion of kinetic energy that is there by secondary reasons, other reasons. For example, convection in the sun, supernova blast waves, and supernova driving motions in galaxy, ISSAA. Those are the reasons that will drive your kinetic energy. Okay, you can tap into those kinetic energies and convert them into a magnetic energy without any electric current at infinity. That's always a guarantee going to give you magnetic. But in astrophysics, you don't have that guarantee. Okay. So this is a self-sustaining process. Yeah. That's called dynamo action. Flow V. So equation look deceptively simple. This is the only thing. That is where you have to explain everything that you see about magnetic field. This flow must host everything about dynamo. Must have all the clues to the dynamo. Okay. Momentum balance also gets modified because of the Lorentz forces. Yeah. Because now we had written everything except this term. Gravity is ignored, suppose. Yeah. But now that there are magnetic fields, they will also exert force on the fluid particles. So this is like a Newton's law of motion. So you add that force contribution in the momentum balance. Okay. So the full system of equation becomes this plus this. Okay. So it's highly technical. We will see. Again, these are observations of magnetic fields over galaxy, and we don't know exactly what is causing it. You can take a box and run a simulation and see that you started off a box here, ended up with this here. Colors are magnetic field. In the beginning, these are very tiny, small scale, right? Scales are very small. Yeah. You can see that colors are changing rapidly. That's what I mean by the small scales. Here, the whole box is filled with the same color. That means the coherent magnetic fields are built up in a box. Yeah. How? Very quickly. So these are the productions of large scale magnetic. So every system which has high Reynolds numbers has roughly two types of, or people try to understand them in terms of two types of dynamos. One is a small scale dynamo. What is a small scale dynamo? And a large scale dynamo. So very quickly, and again you choose your system and the statements apply to any system. Okay? So if I have again this K, which is inverse length scale, small scale, large scale, and energies in kinetic and magnetic field. If this is your kinetic energy scale, suppose this is how I draw. This is K to the minus 5 squared Kolmogorov spectrum. Okay, that's your kinetic energy, suppose. That means the maximum energy is injected at this scale, right? This is the power spectrum. Energy is maximum at this scale. This is a log scale. So this is very large compared to here. So I can actually model it like a delta function because most of the energy is injected only at this scale. So this K injection, okay, this K injection. So this is like a step-like function where you inject energy into the system. Okay, this can be a supernova scale. This can be convection scale. Yeah, this can be a scale over which magnetorotational instabilities work in addition. This stuff like that. Okay, this can be single scale or modeled as a single scale. If you have to use this kinetic energy, this is kinetic energy. From this, you have to make magnetic field, and if you make magnetic field at the scales right of this, which is smaller scale, and if the magnetic field is built here, yeah, it can have its own spectrum. Then you call it a small scale dynamo. If you use this scale and build magnetic field over this scale, say here, this can have its own. You build magnetic field here, this is also EM. Then you call it a large scale. Okay. So it depends on the scale compared to the energy injection scale, based on which you decide the largeness or the smallness of the dynamo. Okay. Most systems have both large and small scale dynamo. Okay. Small scale dynamo has faster growth rate, it grows faster. This has slower growth rate. For galaxy, typical numbers, this will grow as mega year time scale, this will grow at giga year time scale. Okay. So how do we understand this inverse transfer, right? This one could perhaps guess or see in terms of direct cascade or forward cascade. Energy is cascading to the smaller scale. That's a natural way energy progresses and all. How do we understand inverse cascade? Inverse cascade is not, turns out very hard to understand. For example, I can take this, yeah. This is like, say, small, this can be a fluid, yeah. And I'm just looking at a single fluid and I'm injecting energy at the cross section of this. Yeah. So that's a tiny scale compared to this scale, right? So this, imagine this as a system scale, and I'm injecting energy by putting a screw like that. What can happen? This can happen, right? Yeah. So this already something has been produced at the scale of this system. This is nothing but process of energy minimization. As system tries to minimize energy given a constraint, yeah, it can push the fields to a larger length scales so that its energy cost is less. Okay, that is one way to think. Okay, I will show exactly how. Why was I screwing it here like that? This is important, the screw-like motion, is because magnetic field is a pseudo vector. You know the difference between true vector and pseudo vector, right? Yeah. If I take a vector like this, and if I place a mirror here, this vector will look like this. If that is the case, this is a pseudo vector. If I take it like this, and this has a head, and this has a tail, this will look like this, if it is a true vector. Now you take rotation, yeah? Take velocity, velocity is a true vector, curl of u, omega. Yeah? In the mirror, it will look just like that. It will not turn. Okay. Omega is not a true. Yeah? Show that in the. Yeah? Why? That is why I did it. So, if this is your vector, which you apply the right hand rule, right? Right hand rule is what? That you your motion is like this, plane of the mirror is like this. So this motion, which is parallel to the plane, it will not get reversed, right? The motion this will look exactly like this in the mirror also. So your right hand rule will still give you this one here and here, right? So your omega rotation, vorticity, so called. Vorticity did not flip sign because it's a polar vector, or a so-called pseudo vector. Magnetic field is the same. Yeah. Your current J, you can work it out for current again. Yeah. J is curl of B. B is a pseudo vector, and therefore current is a true vector. That's one way to see it. Because you take another curl, it makes it a true vector. Okay. So it's very interesting that certain symmetries has to be broken in turbulence in order for you to produce something which is not a true vector. Magnetic field not being a true vector, it imposes a very strict constraint on the flow. You want to generate it from the flow. If normal flows do not break that symmetry, and if they remain true vector, one could argue simply on the symmetry ground that you will not be able to produce a magnetic field. What is the natural way to break the symmetry in the flow? By having a screw-like motion, helical motion. So if I take a motion which is helical, so if this is a right-handed helicity, in a mirror it will become a left-handed helicity, right? So in mirror, the left became right-handed, or your I cross J was K, it became I cross J is minus K. So if your symmetry in flow has been broken, those flow may be useful, maybe even it's not very clear. But at least that you can argue from symmetry principles that certain symmetry must be broken. Natural way to break is having helicity in the flow. Way to have helicity is also not very hard. Any system which has rotation and stratification is expected to have helical flows. For example, you boil water in a rotating frame, which is what you're doing in any case when you're boiling water on Earth, right? But just imagine very fast rotation. Just go to fast rotating star, and there is a convection which is say some fluid element heated. As it is heated, it becomes lighter. Yeah, thermal expansion of a gas. It lightens up. Now it is low density medium sitting in a high density environment, becomes buoyant. Yeah, Archimedes principle. Yeah. So light density is just rises up. As it rises up, because of the Coriolis force, yeah, omega cross B, because it's a rotating system, Coriolis force will make it rotate. So as you are rising, so you have U Z. Now you got curl in the XY plane. So you put these two motions, superimpose these motions together. So you're rising and rotating. Yeah, like that. That is a helical motion, right? Now that has already naturally broken symmetry. It will look different in the mirror. Left versus right. Yeah. So systems with rotation and stratification will naturally break the symmetry. It so happens that most astrophysical objects are rotating and are stratified. So the turbulence or the flow, which may give you a dynamo, is expected to naturally harbor this property of helical turbulence. Okay. So maybe that is okay. So these simulations involve turbulence which were helical, and that is when you could produce such large scale. If it was not helical, you would see that you will not be able to produce field at the box scale, but at some tiny scale or small scale dynamo, it's still possible. Okay. Fine. How do we try to model them in theory? Okay. That's a bit, it will require much more than just last 5 minutes. Okay. So if you are interested, we can discuss. After all, you are interested in ordered magnetic field, right? So somehow I'm not only interested in the evolution of magnetic field, I'm only interested, suppose, in the evolution of large scale magnetic. Okay, so then you have to filter out your equations. That coarse graining or filtering comes under this formalism called mean field theory, in which any total magnetic field can be split in terms of a mean and fluctuation. Similarly, velocity can be split into mean and fluctuation. It is such that the average of total is mean, average of fluctuation is 0, double average of mean or total is mean itself. These are the so-called Reynolds rule. Averaging can be taken inside the differential operators, okay, or integral. So if I had a quantity like this, I will simply get mean field evolution. So if I take a total induction equation and I average it like this, yeah, I will get an evolution equation for mean field magnet, large scale. Because as I said, I'm only interested in this. How is it that where it is coming from? It must come from small scale motion only, because only at small scale I am injecting energy. So I want to see a source of large scale magnetic field in terms of small scale motions and small scale magnetic. Okay, I'm allowed to see that, right? If you already are driving it at a large scale, that's a separate problem. But my whole interest is in the inverse transfer, inverse cascade. I only have energy at a very tiny scale. This is a big room, and I'm injecting energy at my scale of my hand, or a little bit, like a spoon. Just take a spoon and stir the fluid here, like that. This is what is happening. Supernovae are stirring, just like I'm doing here. Supernovae are actually stirring the galaxy just like that. Every 70 years or so, roughly, there is a supernova explosion. Take a galaxy and make a movie of the galaxy. It will look that, giga-year time scale, right? So large time scale. Supernova will just come like continuously. You see a supernova blasting for a lifetime of the galaxy. That is injecting energy in a galaxy and making it turbulent. Right? So while 70 years look very long, it's very short. It's like just like that. I'm just doing continuously. For a galaxy, this is what it will look. And everywhere, homogeneously. So everywhere, all around this spiral arms galaxy, everywhere supernova going off like that, like that, like that, like that, and making the fluid turbulent. That is the energy available at that scale. You have to use that and make a magnetic field at these scales. Yeah. So if my interest is such that I am interested in evolution of this large scale field by interactions at small scales, I could employ this so-called mean field theory. You work it out, you will have a term like this, right? E cross B. This is the term. Now I'm writing prime for total. Okay. So you will have V cross B. Take the average and note the Reynolds rules. You will have quantity which is made up of totally mean field quantities and a quantity which is totally made up of small scale quantities. Right. So that's to do with correlations. That I can have a quantity whose average is 0, but the product of that need not be 0. Right? Kinetic energy is a very simple example. Right? It's a second moment approach. I take a velocity field, I take an average, that can be 0 for a turbulent or stochastic field. I can go, that's the first moment. Right? I can go to the second moment, energy density. That is not equal to 0. In fact, that is the kinetic energy. Right? It's like twice kinetic energy, isn't it? So just imagine that I have a time series over a function of time. There is a velocity field which is just going plus and minus. If I take an average, I get 0. But if I take square and then take average, it is not 0. So it's something like that. Not exactly, but something. So these quantities, which are individually 0 when average hits on them, small v and small b, their correlations may survive. Okay, that is what we are looking for. That can act as a source term for your mean field equation. Okay, which is totally made. It is called the mean electromotive force, which is made up of only small scale. That's why it's written small v and small b. Capital B is large scale. So large scale field being evolved entirely by quantities made up at small scales. That is what we are looking for, right? If there is a possibility, but it's a very hard problem because in order to know the evolution of this, you are required to know this mean EMF. In order to know this, even if you assume a helical flow, suppose flow is given to you, that's called a kinematic problem. Okay? Suppose flow is granted, so don't worry about it. Yet, in order to know the source term here, you need to know small b here. Yeah, how do you know small b? So you have a total equation for the total field. Now you have derived an equation for the mean field. you subtract B prime minus capital B, you get the equation for small b, right? I can do that, and I get this term. I'm just trying to show you a hint of infinite hierarchy of equations and how the closure and everything appear in equations. Okay. The problem looks simple, that this can give you this. Okay, that's one level. That requires a small b. Equation of that involves the same b. You see? So what do we do now? So that is the problem. Now you try to substitute here. In principle, you can see that this will involve an infinite. This is not two equations. This is an infinite number of equations. Okay. 2-point function will depend on 3-point function. 3-point function will depend on 4-point function. 4-point function will depend on 5-point function. Isn't it? This is a single point dependent on 2-point. If you want to naively see small b will involve further 2 points, right? Or just, even if you ignore everything, just here, small b I can write as small b cross b. So that became like 2-point here. That is a second order to it. That is what most people do. But you can see that this b can involve another 2-point here. So it becomes 3, 3 becomes 4, 4 becomes 5. So these are actually infinite set of equations. Okay? What do we do? But the disturbance nature of this. Yeah? So quite often, and this is non-linear in fluctuation, while the equation look linear, this is non-linear in fluctuation. This is a stochastic variable, this is a stochastic variable, product becomes non-linear in stochastic variable. Okay? So non-linearity is there, but looks different. So what one typically does, okay, it's a very dangerous step to take, but you just simply throw it and say that I will stop. It's like my equation is such that you quite often are writing equations that f of x is, say, a plus bx plus cx square plus bx cube, yeah, an infinite number of equations. That is the nature of this. And without really offering any justification, okay, what one is saying that I will stop at this level. I'll just throw it and I'll stop here. Okay, that's the kind of thing one does and calls it closure. Okay, one has to close the equation. After all, one has to make some progress. Yeah, so you close the equation at some point. You truncate the series. It may be valid, but it may not be valid for astrophysics. So theories are possible or tractable when you do such a drastic step. It's good, but the only problem is that it may not apply to the real astrophysics. So while one is allowed to do this, but this is now very fashionable today that people overstate their results. Yeah, they don't tell you this. Okay. So, and regardless of field, that by and large, it is a culture now that to overstate the results. Okay, without even testing the regime of validity. Okay, so we don't know. Okay, at least I will not say that I know. But this is what I can do, so I will do it. Okay, and then having ignored this, small b can be solved for. You throw away this capital B, and then it is not such a hard problem. Okay, then it can be done. You can do better certainly, but you will find that things become harder and harder. And then even if you do, you will not be able to understand. Okay, so that's another problem. What is the point of writing a very big equation when I can't make any head and tail out of it? It might be correct, but I just don't understand. So it remains as complex as the system itself. So you have, in principle, a solution which is a series solution, which I cannot sum in any closed form. Yeah? If somebody has told you that this is a series x, some coefficient x cube, x power 5, something, and you didn't realize that this is just a sine x. So you didn't understand properly. Yeah? So only when you can sum the series and put it in some closed form, only then those solutions could mean something. Just having solution is also not enough. Okay? Overstating is dangerous, but that is a culture. Okay. So let's stick to the culture, and then you can see that this E I can write as small b cross b. B I can write, forget about the other terms. I can argue. So this small b can be written as small b into b. B can be taken out of the mean because b is already in mean quantity. It is called timely produced ones. It's timely. I can take a mean field, okay, and I can hit a small scale motion on that, and it will produce a small scale magnetic field. Okay, so that is coming from this sort of timing, that there is a mean magnetic field small v acts on that, produces a noise, magnetic noise. So I get v small v. So the 2-point velocity correlators that become the origin of all your dynamo and dissipation. Oh, it comes with turbulent dissipation. That is what is dissipating, say, in this room, and that is what we discussed before. This is what we did not discuss before. Okay, this will always kill, but this can give you a dynamo. This is, as you see, v dot omega. Normally, one thinks that curl of v and v dot, they must be zero, right? Curl of v should point in plane perpendicular to v. All that doesn't work. These are space quantities. Yeah, the curl, when you are taking a curl, you can't actually flow like this. You cannot actually close your hand. It is only possible when you take the curl of a field in a 2-dimension such that you can actually close your hand to define your this vector. And then you can say that the field that is lying in this plane is perpendicular to this vector and v dot omega is zero. But this is a helical flow, so your finger will turn. It should go like that. It should not close here in the same plane. So change the plane. So v dot omega, as I argued, for helical motion can be finite. Yeah. Alpha is therefore a pseudo vector, and now in principle it's looking good that you have a pseudo vector that you want to generate. You have a pseudo scalar that is there because of the property of turbulence that helicity might be present, and then maybe that can lead to a dynamo. Okay, where it is leading to a dynamo from, it is exactly this term, right? That term will be there. This is the term that is making this large scale magnetic field. This term involves entirely the flow. Small v can be written in terms of capital V. So the whole thing is produced by only the velocity. Yeah, it's very remarkable, right? Small v dot curl v. V is just coming from motion that we are reciting from supernova and everything. That alpha, so long as it is finite, can give you magnetic field straight away. So that's where the linkage is. Conversion of kinetic energy into magnetic. Yeah. At least you see the paths, right? And where it is going. If you are more interested, you can look up this review article. This is a very fundamental event. Even the systems are hard, it is useful always, regardless of the field, regardless of MHD or something. It is always a very useful thing to come up or look for invariants of the problem. Okay? So that even if I don't understand something in detail, yeah, I know that it must evolve under this constraint. Helicity offers such a constraint. It turns out that the magnetic helicity, which is defined in terms of magnetic vector potential, because divergence of B being zero, we can always be written in terms of vector potential curl of A, right? If you take the dot product of A with B, A dot B, it turns out to be ideal invariant of the problem. Eta is very small, right? But dH by dt is zero. It behaves resistively, which means even if it is finite, it's been tested that this paper has essentially tested that nearly conserved for even high magnetic resonance in the system. Okay. So if that is the case, then magnetic fields must evolve in a very bihelical manner. That I started off with very small magnetic helicity. Helicity is again like an internal twist in the magnetic field that you can try to imagine. Helicity is always some twist and some imaginary space involved. So you imagine that in terms of a twist. So as soon as I try to twist them, I see that this is. We have another picture. Okay, I don't have. Fine. At least one thing one can see, the energy and helicity in Fourier space are related by something like magnetic energy in a Fourier mode K goes as K times magnetic helicity. Okay. So if helicity is to remain same, I want to have the same kind of helicity. The way to minimize energy is to push the field to a smaller and smaller K. That you can see. You can work it out from dimensions, but I'm just saying why large scale fields can be preferred in nature. It's simply because of some sort of helicity conservation. That if you, so again, that's like to conserve this, you don't vary this, but you want to minimize the system, wants to relax. So relaxation may involve putting the energy to a lower K, right? lowercase larger scale, and that's one way to think of origins of large scale magnetic fields in the universe. This is all system independent. Okay. It has to be bihelical. What do I mean by bihelical? Is that if I have started from zero magnetic helicity, I cannot produce net, but it can be sign quantity, plus and minus, right-handed helicity, left-handed helicity. So as soon as I have created some internal twist by motions, there must be some large scale field which must have a helicity which should cancel the internal helicity. So you can have a helicity distribution in scale. So the spectrum of helicity should show one sign on large scale, other sign on a small scale, so that the net remains zero. You started off with zero, you remain zero, because you would not have produced the net, but you could redistribute in spectral space. So that is where you also see the richness in the spectral space, that you start to analyze quantities in the spectral space. This is called the spectral space. In a wave number, you take Fourier mode and just see. This is a positive definite quantity, but it showed you certain spectrum and everything, revealed itself. When you plot for the magnetic helicity, you will find that this is plus plus at this, minus minus at this. This is the scale at which suppose the sign changes. So this is like a large scale dynamo with plus helicity. This is a small scale plate, not dynamo, but this is a small scale magnetic field with a negative helicity. Yeah? Negative helicity. Net was zero. And the net is zero because of the constraint coming from helicity conservation. Now, systems, natural system can have fluxes. That's like solar wind carrying away the helicity. If I want to twist my hand beyond, and I don't want to break it, but yeah, the reason that I can't twist it further because the internal stresses are very large, very strong. Right? That leads to the saturation of the hand. Yeah, once we start to grow, these are linear systems, right? Any system, any equation which looks linear, if it grows or decays, it will do so exponentially, right? Why? I have a system which is some sort of a d of a f, dt, and on the other side is some function times f itself. Okay? Yeah, I can always write it as solution in t will be exponential in nature, right? Yeah. It's a very crude way of saying, but if you are looking at some sort of homogeneous equation, each term involves f, which is the case with induction equation, right? I can imagine a solution, yeah, a family of solutions, where f as a function of time will go as exponential to the g2. G has positive eigenvalues. This is a matrix. This is a vector. Yeah, it's written in some sort of matrix notional form. This matrix, if it has a positive eigenvalue, can grow. Right? The reason I want to show is that it will have an exponential growth. Where will it stop? Yeah, it has to stop somewhere. Yeah, it's drawing energy from the kinetic energy. After all, you cannot throw much more than the U particles. There is so much energy available in kinetic motions. Supernova has given you only so much energy. You cannot draw more than that, right? So there is some constraint comes. Somewhere you have to saturate. So the way to see saturation is by turn your hand. Somewhere you stop because the internal distresses will stop further twist. Okay. If you want to twist further, you have to remove that. Okay. So sometimes the dynamo you see can saturate at a very small values. But if you want to explain larger values, say for the sun, you are not happy with the saturated magnetic field, you want to increase its value, the level. Then what is happening from solar cycle to solar cycle, perhaps. Some solar cycles show very large magnetic fields, stronger values. Some cycles show smaller values. What might be going on? It's not very difficult, at least to imagine. Is that I want to, sorry.
You want to finish?
I want to finish it. They also want to go out. No, so I want to twist it further. I remove the internal stresses that can happen through winds. So when there is a solar wind, they can carry with them the internal stresses or small scale magnetic felicities, which are these objects here. Small scale magnetic felicity at large scale that can be carried away and thrown out of the system. Then you are relieved of the pressure and you can just twist it a little bit further, and that further twist will give you larger and larger magnetic. So you can build the saturated strength. As you saturate, the saturation level itself can be made larger if you allow for fluxes of small scale magnetic. So I've said enough. Okay, if you are interested, we talk. I think you're all tired, right? Yeah. So any questions? Today was math.
Online.
Ah.